halo, and most of the stars that would be in the disk of our galaxy were born in the disk itself. So actually, if you're trying to reconstruct merger history, then you can look at the stellar halo, and the stars that you see, actually the prediction would be that a fair fraction of these formed in these building blocks at high redshift. And so what's interesting is that you could try to find, say, how many objects were put together to produce the stellar halo of the Milky Way. When did this happen? How important mergers were? And what I find particularly interesting is that we're really studying stars that are very nearby to understand what the properties of galaxies were at very early times in a very different way from how we're used to doing by observing directly galaxies at high redshift, for example, with HST. So why can we do this? We can do this because stars are fossils. They actually remember where they come from. And they remember this in their ages and chemical composition, because stars remember the chemical composition of the molecular cloud in which they were formed for most of the time, their lifetimes. But also stars that were born in a similar system, they move together through space, so there's memory in their motion, and they might define substructures. So in this sense, galactic archaeology, if you want to do galactic archaeology, the best place to look for the signatures of the history of the Milky Way is really the stellar halo. So having set the scene, what I want to describe is some of the very first findings that we made with the second data release from the Gaia mission. So I'm going to go through some very simple HR diagrams that actually already showed the quality of the data and showed some very surprising results on the galaxy. And then I'm going to focus on the kinematics of stars in the Milky Way, on the disk, and then on the halo. And this is really possible, this was really possible thanks to the work of the Gaia collaboration, DPAC, which is an ensemble of about 500 people, 500 astronomers and engineers in Europe at different institutions, all under the hood of Anthony Brown, who's the chair of DPAC. And we've worked really, really hard to get the data release on time without actually looking much at the data itself. Because as a consortium, and I'm part of this consortium, we were actually not allowed to do any science exploitation of the data. So there were 6 papers that were produced at the time, which are science verification papers, which, and I'll show some results about one of them, this one, today, which were basically the only thing you could do is you could make a simple diagram that was scientifically meaningful, just to look at what is the quality of the data, what are the limitations, so that actually the rest of the community knows about these things. But you had to stop there. That was the deal. So it was a lot of work, and it's amazing that actually the community, all of DPAC, we're very committed to making Gaia a success and to having as many people work on the data set to learn about the galaxy. Yes, and then the work on the disk was led by Teresa Antoya, who's a postdoc in Barcelona, former postdoc of mine. And then there's a lot of work that I'm presenting on the halo and the thick disk, and has been led by Helmi Poppelman, who's a PhD student in Groningen, together with Davide Massari. Okay, so let me show you, go right to the data. So because you have now the parallaxes of so many stars, you can actually compute the distances to the stars, or you can compute an absolute magnitude to the stars. So you can construct an HR diagram. So usually what we do is we have color magnitude diagrams, but now we have distance. So we have absolute magnitude versus color, and this is for a nearby sample of stars, and you can beautifully see the different phases of stellar evolution. We see sequences on the white dwarf sequence. But I think what I found at least very interesting is that you can also combine this with kinematics. And then, so if you look at a sample of stars that have tangential velocities, these velocities with respect to the sun, which are similar, which are low, so these stars are moving like the sun itself, basically, so they are in the thin disk of the galaxy. Then you get this HR diagram. If you allow for slightly higher tangential motions, you would be probing the thick disk, right? So these have orbits that are more different from those of the sun. And then if you look into the realms of the halo, so you're looking at stars that have very different velocities from the sun, and you're looking into the halo. And just this simple diagram actually shows, this HR diagram shows two sequences, and this was not known, actually. So the fact that you're seeing in the halo population, you're seeing basically two rather prominent sequences on the, say, the turnoff, the main sequence, also on the giant branch. That tells you that the halo near the sun is dominated by two components. And we didn't know this was the case.
Also, the rapidly moving ones, you have a connection between those two branches.
Right, yes. So what are they? So then we looked at the kinematics themselves, but I'll come back to that. This is, I think, one of the first most important results showing that actually there was something hidden in the halo near the sun for us to discover. So let me now move on to the disk of the Milky Way. So like I said, Gaia has produced a data set that has proper motions from these 1.5 billion sources, but only radial velocities for 7 million. And so only for those you have full phase space information. And so this is what I'm focusing on now. So this is the distribution of stars for this 6D sample. What we used to probe in the past is marked by this circle. So this is from the Hipparcos mission. This is what we knew something like 20 years ago. And so you can see that now, even on data release 2, we're probing a much larger volume with very high, very small velocity errors of 1.5 kilometers a second. So let me just get on the same page with you on what are the velocities, because we'll see lots of velocity information. So we have the galactic center here, the sun here. Then V5, the V5 velocity denotes rotation around the galactic center in the plane. Vz is perpendicular to the plane. And VR denotes in the radial direction in the plane, right? So what you can do is you can look at all of the stars here in a volume like this around the sun, and this was the state of the art before Gaia DR2. So what I'm plotting here is the radial velocity in the plane against the velocity in the sense of rotation, and what you see is some substructure. And you see some bimodality here, so you see a feature here at low velocity and a main component here. And this feature was known and believed to be due to the bar of the Milky Way through a resonance process. So one of the first things that we did was to plot this for the same sample, so very nearby stars. And this is the same diagram that I was showing. So radial velocity against V5. And this is the lower branch and the upper branch. And you can now clearly see there's a valley in between. But you can see also a lot more. There's a lot more structure in this diagram than there was before. You can see arcs. You can see structures. You can also see shells if you look at the other components. So this is V5 versus Vz. So we see features, very sharp features, and also if we look at VZ versus VR, we also see very, very sharp features. So we knew about the bimodality caused by the bar, but we were surprised to find so much structure, and it felt as if suddenly you were putting your glasses on and seeing sharp. So what is the rest? Why are we seeing so much structure? So as soon as you see a shell and you're a dynamicist, you get excited and you think, okay, I'm going to do a phase-based diagram. And that is, you're going to plot, for example, the z velocity as a function of position above the plane, so as a function of z. And when we did that, we found this. So what you're seeing here, I hope you can see, it's like a snail shell pattern. And this is a trademark of phase mixing. Now, phase mixing is a very common phenomenon in dynamics, which is if you take a group of stars and you let them evolve in some potential, they will mix away, and you make a diagram like this. Say a coordinate versus the velocity in that coordinate, and you'll see a shell like this. Now the question is, why are we seeing this if this is happening all the time in the galaxy, right? Why are we seeing this in the data? So it turns out that if you actually displace slightly the disk in position, so from the plane, you displace it slightly, and you give it a small kick of about a few kilometers a second, and you look at that patch of the disk, how it evolves with time, then after 10 million years, the distribution of stars is like this. After 100, it's like this. After 200, it's like this. And if you wait 500 million years, then you get this shell pattern. So what does it mean, actually, that we are seeing this? It means that the disk of a galaxy near the sun was sort of kicked about 500 million years ago, and what we're seeing is kind of how that happened. We can tell the time scale from the separation between these different wraps. And so then you ask yourself, okay, but what caused this? And it turns out that there is this tiny galaxy known as the Sagittarius Dwarf Galaxy that had a passage about 500 million